Welcome to a lesson on gravity and orbits. We're going to go through this today, but we're also going to have a quick recap on last lesson's work. So we'll go to the visualizer first, and then we'll have a recap and we'll have a look at what else we need to learn today. Okay, so last lesson we learnt about the solar system, and there are a few different facts that we needed to know. So historically, a guy called Ptolemy, a scientist, he believed that the solar system was a geocentric model. So geo meaning Earth, so it was an Earth-centered model, which means that everything else went around the Earth. So he had this idea that Earth was at the center, the moon would go around the Earth, and then you'd have all the other planets going around the Earth, and eventually you would have the sun going around the Earth as well. Now that was really popular with the Catholic Church because it meant that the Earth was special. The Earth was right at the centre of the solar system, in fact the centre of the universe as far as they were concerned, and everything else went around it. Now, after a while, this was less accepted because a man called Galileo came along with one of the first telescopes, and he looked through the telescope and he could see Jupiter and its great red spot. And some days that he was watching it, he noticed that black shadows would move across the surface of Jupiter, and he could track them. And he realised that actually these shadows were the moons of Jupiter that were orbiting Jupiter itself. So using his telescope, he was able to determine that these moons orbited Jupiter, and it wasn't that everything went round the Earth, because that was what was suggested here. If everything went around the Earth, then these moons would not orbit Jupiter, they would orbit the Earth. So Galileo was one of the first to suggest this. But after Galileo, and this is the kind of the guy we credit it more to, is Copernicus. And Copernicus came up with the heliocentric model. Now, helio stands for sun. Helios is the Latin for sun. So heliocentric means a sun-centered model. And that's far more what we believe these days. So there's the sun, then we have Mercury, and then Venus, etc., etc. And we'll come back to that in a moment. So those are our two models. We've got the heliocentric, which is the one we believe these days, Copernicus, Galileo, who found it, and Ptolemy, who believed in the geocentric model. And actually, we don't discount this geocentric model because it's a really good way of modelling exactly what the stars and what the planets are going to do. So when we have our models of the solar system and we want to look at where that planet would be if we looked up in the night sky, we still use Ptolemy's model because this was perfect for those observations. It's just not true for what's going on in the solar system. The heliocentric model has the sun at the centre. So that's sort of the history of the solar system, and hopefully you picked that up last time. Let's go through what we know about the solar system. Well, we start at the centre with our sun, and as we know, that is a fusion process, and it's emitting light energy and thermal energy, which is allowing us to live on Earth, basically. We've then got Mercury, Venus, Earth, Mars, Jupiter, Uranus, Saturn, Neptune, and I'll put good old Pluto in brackets down here because sometimes it's a planet, sometimes it's not. We probably these days should call it a dwarf planet, which means it's a small planet that hasn't really got its own orbit. Now, Jupiter, Uranus, Saturn and Neptune are all gas giants, which which means they are mostly gaseous. Jupiter is the largest in our planet. Believe it could have potentially been another star. Don't know. Didn't happen to fuse, so therefore it's got lots of hydrocarbons and things like that on it. And Saturn obviously has rings. What else can I tell you? Uranus has a very strange rotation. So the Earth has a rotation that's sort of like this, where it goes around that way. Uranus, ooh, that's a terrible diagram, has a rotation that goes like that. And in fact, Uranus's planetary rotation takes longer than it takes for Uranus's year for it to go round the Sun. So we've got quite a few different bodies within the solar system that we need to know about, and that's really important you know that order. There were two other objects that we had to consider in our solar system, in fact 3 other ones. Asteroids. Now asteroids are rocky objects and they orbit the Sun. They become meteorites when they hit the atmosphere and start to burn up. We have comets, which are balls of ice, well, rock and ice, and they will in fact outgas. So you'll probably see a comet drawn like that, where that is the Sun. Because of the Sun's heat energy is hitting the comet, it's losing some of its ice, and that's causing it to outgas, and you get this nice long tail behind it. So comets have very interesting orbits. The comet's orbit sort of looks like that, where it's very, very slow around this part here, which we call the Oort cloud. This is where they sort of exist right on the edge of the solar system. And as it gets closer to the Sun, it's getting closer and closer and closer. It gets faster and faster and faster, always with the tail pointing away from the Sun. So even here, once it's gone past the Sun, if it's going around in that direction, the tail would still point away, and the tail gets smaller the further away you get, because there's less energy to cause the ice to melt and become outgas. Okay, so comets we've dealt with, asteroids, comets, and the last thing we need to cover is natural satellites. And we have one natural satellite around the Earth, and that is the Moon. There are numerous around Jupiter, there's numerous around Saturn, 3 or 4 around Mars. Moons, they are natural objects that orbit the planet. Okay, so they orbit the planet, but they are also natural objects, hence the natural satellite. A normal satellite would be something that would deliver your Sky TV. Okay, so the last little bit we've got to talk about is astronomy. And we have changed our methods over time. So in the past, we had scientists who would take photographs. So in fact, before that, we would just have people's observations. So you would have Galileo, here he is, looking through his telescope, and he would draw down what he saw. So not very accurate. We go beyond that, and we might have still a telescope, but we have attached a sort of old school camera, so photographic film, and they would then have to look at the photographic film to work out what has happened. So there'd be numerous photographic films, and in fact these were the first computers, which is a really interesting story if you look it up, because it's the marginalised in American society who were asked to go and be these computers. So it's black ladies who would spend their time looking at these pictures to work out what was different. So these were human computers. And then more recently, we've now got really big kind of telescopes, sort of looking like this, that can rotate. They're in very big buildings, but they will be attached to what we now modernly call computers. But we also have telescopes that are in space with solar panels, the Hubble being one of those, and the James Webb, if it ever gets made, will be another one. and those are fantastic because there is no atmosphere to get in the way, and in fact they can take pictures all day long. We also have to remember that the atmosphere will absorb some of the EM spectrum. So if we put them into outer space, we can absorb some of those, we can observe some of those rays of light, some of those frequencies and wavelengths that we wouldn't be able to observe on Earth. So you can put X-ray telescopes up there, which give far more interesting pictures than just visible ones. Or we can have thermal pictures, we can go infrared, we can look at gamma ray, we can look at the whole spectrum. So there's far more information being detected in space than you would necessarily get on Earth. However, on Earth, we can still do radio telescopes and visual telescopes. So there are still some interesting ways of detecting on Earth. Okay, so that's our recap. We've gone back through the previous lesson, and let's now go to today's lesson. So it's SP7B, it's gravity and orbits, and I'm going to point out the points where I would like you to take some notes, and in fact try and take some notes on everything that we talk through because it's all important. Okay, so SP7B, gravity and orbits. 6 different things we need to be able to do in this lesson. So we need to be able to recall the factors that affect the strength of a gravitational field. We need to explain why G has different values on different bodies in the solar system. Describe the orbits of moons and planets, comets and artificial satellites. Explain why the velocity of a planet changes even if orbiting at a steady speed. Describe how changing the speed of an orbiting body affects the radius of its orbit, and explain how the radius of a stable orbit is affected by the orbital speed. So lots of sort of bits about orbital mechanics in this lesson. Okay, so gravitational field strength actually depends upon 2 different factors. The first factor is the mass of the object. So anything that has mass, any object that has mass, has its own small gravitational field strength. So that pen you're holding in your hand is slightly attracted to you because you both have masses. You are both exerting your own gravitational fields. Now they're so small because the masses are so small. But when we scale it up to sizes like the Earth, the Sun, objects that have, or in fact even the Moon, which is nowhere near the size of the Earth, objects that have enough mass have a gravitational field strength that's detectable. Now the other thing that it depends upon is the distance between the 2 objects. If you stand really close to the Earth, you've got a much stronger gravitational field strength than if you're out in space. And in fact, if you go to the International Space Station, it gets so small that it can be counteracted by the speed at which you're orbiting the Earth, hence you become weightless. So if you were to climb to the top of Everest, you would have a smaller gravitational field strength, a smaller gravity field pulling you down than you would right here at sea level. And obviously if you get closer to the centre of the Earth, get closer to the larger amount of mass, then in fact your gravitational field strength would increase. A bit strange talking about that, getting closer to the Earth, because obviously you would end up with mass around you as well, and it becomes more complicated in that respect. So 2 really important concepts that we need to consider. Okay, so let's write ourselves some notes. So gravitational field strength, which is what we would call gravity, really. It's much better to call it a field because it is acting downwards, it's pulling you onto the planet. It's affected by 2 things. It's affected by mass, and it is affected by distance. So the bigger the mass, so big mass will lead to a big gravitational field strength. So a small mass will lead to a small gravitational field strength, and a big distance, so if we're increasing the distance between 2 objects, it will lead to a small gravitational field strength, and a small distance will lead to a large gravitational field strength. So we're talking about having big masses, little masses. So this might be the Earth, the Moon. Obviously the Earth has got a greater mass, so therefore it would have a greater gravitational field strength. And we're talking about distances, so two masses the same that are close, or two masses that are really distant. Looking at the distance between them, in fact it would be between the centres of them, but let's not worry too much about that. This one would have a much smaller gravitational field strength. This one would be bigger. And if I've got a big mass and a small mass, then this would have a big gravitational field strength, and this would have a small gravitational field strength. Okay, so I'll go back to PowerPoint. So we've recalled that the factors that affect the strength of the gravitational field, there's two factors, we need to consider them. And I just want to introduce you to an equation that you come across in A level. You don't need to know this, but this is the idea of being able to measure or calculate our gravitational field strength, this G. It's equal to this constant, big G, which Einstein came up with, multiplied by two lots of the masses, so mass 1 and mass 2, all divided by the square of the distance. So you can see here that if m gets bigger, either of the m's gets bigger, then g gets bigger, and if r gets bigger, then g gets smaller. Now you don't need to know that equation, but I thought it'd be nice to introduce you to it to show you what it's about. Okay, so we're going to pause the YouTube video in a moment, and you're going to have a go at answering this question. But can you explain why Mars has a greater gravitational field strength than the Moon? And if you can write it in full sentences, that would be fantastic. So pause the YouTube video here, have a go at answering it. It should only be one sentence and potentially 1 or 2 marks in an exam. Okay, hopefully you're back now and you've had a go at that question. So let's have a look at the model answer. So Mars has a greater gravitational field strength than the Moon because Mars has a greater mass than the Moon. It's as straightforward as that. One of the two constants two variables we were looking at before with regards to gravitational field strength, and we need to describe it in terms of those values. So let's have a look at another one. Explain why Jupiter has a greater gravitational field strength than Mars. Okay, so pause the YouTube video here. Following the same process that we've done on the previous one, can you explain, and looking at the pictures as well if you don't know, but why does Jupiter have a greater gravitational field strength? Okay, well done. Hopefully you've come back and you've got an answer. So Jupiter has a greater gravitational field strength than Mars because Jupiter has a greater mass than Mars. What about if we considered it in terms of distance from the Sun? Which of these two would have a greater field strength from the Sun due to its distance? Well, hopefully you were just thinking about that and you should have thought Mars, because Mars is closer than Jupiter. And remember, the distance is the closer you are to the source of the gravitational field strength, the stronger that field is going to be. Okay, so in this case, Mars would. What about between Mars and Mercury? Well, in that case, it's going to be Mercury because Mercury is closer than Mars. But obviously that would also take into account the size of the mass of the planets. So bear that in mind because it's not just as straightforward as the distance. We consider the masses, but you don't need to worry about that too much until we get to A level. Okay, so going back to the visualizer for a moment, we've looked at all of this before because we know that gravitational field strength can actually give us a different calculation. Hopefully you remember from the first topic, or one of the first topics we did, W equals m times g, where the weight of an object measured in newtons is equal to the mass, which is kilograms, multiplied by the gravitational field strength, which is newtons per kilogram. So that means that we can work out the weight depending upon the gravity. So if we now go back to that previous question, which you can sort of see up here somewhere, Jupiter has a greater gravitational field strength. So if I took 10 kilogram mass and put them on Mars or Jupiter, which one would have a greater weight? Well, it's going to be Jupiter because that gravitational field strength is going to be bigger. So let's just have a look at some values so you can see the gravitational field strength of Earth. So we'll call it G Earth, is 9.81 newtons per kilogram. The gravitational field strength on the moon, which we know is a lot smaller, is 1.62 newtons per kilogram. So knowing that information, you could be asked to say which of these two planets has the lowest mass. Well, it would be the moon, because the moon has the lowest gravitational field strength. If it was which is closest to the source that we're measuring this gravitational field strength from, then it would be the Earth. Because if you're on the ground of the Earth, it'd be 9.81. If you're on the ground of the moon, it'd be 1.62. So you could then, depending on what information you want from it, you can work it out. So it all depends upon the mass and the distance between the two objects. Okay, so back to the PowerPoint for a second. So we have now explained why G has different values on different bodies in the solar system. So we've covered 2 of our learning objectives so far in this lesson. So let's look at orbits now. So hopefully you remember from the first lesson that planets orbit in a circular motion. They have a circular orbit. It's not quite true. There's also a bit of what we call eccentricity, which means that it's a bit more oval rather than being circular. But what you do need to know is that comets have a high eccentricity, which means they are very oval. So this comet gets much closer to the sun this side of the orbit than it does at this side, which we talked about right at the beginning. So comets have a non-circular or oval orbit. Okay, so quite important to know that. Now we can also put satellites in orbit around the Earth. This is quite an important diagram, so I would recommend that you take almost a copy of this or take some notes of this, but I'll talk it through now and you can pause as you need to. So let's look at this green orbit here. So this green orbit is highly elliptical, which means that it's quite oval. It means it goes much further away at one side of the orbit than the other. And this is what we would call a polar orbit because it is going over the poles and generally used for communication. And that's because you can cover quite a bit of the Earth with it. Okay, so that's not quite a polar orbit, but it's on an angle that's close to the poles. If we look at the purple orbit here, this is going directly over both poles, and these are usually used for spying satellites. So these are the kind of satellites where you can look at anything across the world. So as the world spins underneath, a satellite in this purple orbit could in fact take a picture of any point of the Earth at some point in its orbit. We then have, let's do the red ones first. We have the red orbit here, which is what we call the low Earth orbit. So you need the least fuel to get your satellites at this point here. But notice the satellites have to move around 7,500 meters per second. So quite a significant velocity to actually keep moving at that in that orbit. And then these blue ones, which are the really important ones, these are known as our geostationary orbits. And our geostationary orbit, in fact, will take as long to go round the Earth as the Earth takes to spin on its axis. So that means that those satellites appear to stay in the same spot in the sky. Now we use those for broadcasting because I don't know if you've ever noticed, but if you've got satellite TV or Sky TV, you don't have to move the dish. If the satellite was moving relative to you, you would have to move that dish, and that would be quite problematic. So instead what we do is we put those satellites into this geostationary orbit. As long as when the satellite man has come to set your satellite up, he's pointed at the right satellite, it will stay in that position and will broadcast from there. Okay, so these are a very, very long way away, but that means that they stay in one spot. So they're very good for weather satellites, they're very good for communication, TV, all sorts of things like that. Okay, so we've covered those orbits. Make sure you've got some information of that down. So we've described the orbits of moons, planets, comets, and artificial satellites now. Okay, so what about if we want to change orbits? And this is where we're going to look at a little simulation. Okay, so we're now going to have a look at what happens to satellites as it changes its speed. And we're going to use a simulation to do this. I put the link here so you can use it as well. You can go and have a play with it. And we're going to have a look at it together. So let's shift to the simulation here. Okay, so what we've got a model of the Earth. We've got a small satellite, which is this white bigger block here in the center. We can see the force of the Earth on the satellite, Newton's second law of pairs. Remember, there'd be a force of this, so force of Earth on satellite, force of satellite on Earth, and they would be balanced. And we've got a velocity because our satellite is moving around the Earth. So we'll start by just running this simulation. We can see our speed is around 8,000 meters per second, which we know is a low Earth orbit because we learnt that in a previous little bit there. The orbit radius is, so this is from the center of the Earth, it is 6.4 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. And we've got a mass of the satellite. Now let's just stop that for a second. As one of the points we had to learn today was to know why the velocity was changing even though the speed wasn't. Well, remember that velocity is a vector, which means it has a direction and a size. In this case, the size is remaining constant, so the speed remains around 8,000 meters per second, but as it's rotating, what do we notice? We notice that the direction changes. And that's why there must be this force, because if there's a change of velocity in time, there must be an acceleration. And if there's a mass and an acceleration, Newton's second law tells us that there must be a force. So this is the centripetal force, which is acting towards the center of our planet. Okay, so let's restart this now. So I'm going to increase the radius a little bit. In fact, we're going to try and put it into geostationary orbit. And if we remember from the previous slide, we have found out we need to be about 3,070, can I get it? 3,080 meters per second to stay in geosynchronous orbit. So before we're about 8,000 meters per second and we were quite close to Earth, so in a low Earth orbit. Now we're about 3,080 meters per second and we are in a geostationary or geosynchronous orbit. We're going to call it geostationary. So you can see that if we reduce the velocity, we're able to have a greater orbital distance. So what's going to happen if we slow these down? So here we are, we're in a geosynchronous orbit at 3,000 meters per second. I'm going to drop it to 2,000. What's going to happen? See if you can make your prediction. So we'll drop it right down to 2,000. Do we notice how the orbit is what we call decaying? This satellite is no longer staying in its geosynchronous orbit. In fact, it is dropping towards the Earth and it's picking up speed because it's gaining kinetic energy. What's going to happen eventually? Well, the satellite will find a new, potentially it will find a new stable orbit. It may not be circular, it's probably likely to be elliptical, and we can see it's coming almost all the way back out to our geostationary orbit. In fact, it pretty much crosses it, which is great. But now we're in a highly elliptical orbit, and every time it's slowing down, let's slow it down a little bit more, we are finding it is getting closer and closer to the Earth. So if the velocity decreases, oh, we've lost our satellite, it's gone. The velocity decreases, then it no longer has the speed it needs to keep orbiting the Earth. Let's look at that once more. We'll do it with our standard here in a low Earth orbit. So we're at 8,000 meters per second. What about if I drop it to 6,000? Well, it's going to crash because it doesn't have the velocity to keep going around the Earth in an orbit. So it decays from that orbit. Now, any satellites that get close enough to the Earth will in fact start to slow down due to the friction of the atmosphere acting on the satellite. So it causes an extra force, an extra deceleration on that satellite, which means it's going to slow down quicker, which means it's going to crash quicker. Okay, so we have covered everything we need to cover in this lesson. So I'm going to leave you with this task here, which is to have a look at this SP7B2, which I attached to the assignment. It's all about orbital speeds. So I'd like you to calculate the distance the planet travels in one orbit. If you know its radius, how do you know how far it travels in one orbit? Well, think very carefully about what you know from your maths. Okay, it's a circle, so see if you can remember. If you need some more help, you know to contact us through email at the Hedingham email address. So we're going to convert each orbit into seconds, so time period. You've got the period here, it's in years, so you have to convert to seconds, and then use distances and times to work out a speed of each planet in meters per second. So I would suggest you draw this table and put 2 or 3 more columns on. You might want a column for the distance they're traveling, a column for orbital period in seconds, and a column for orbital speed. Then you need to plot a graph. Now, if you have no graph paper, see if you can do it in Excel. Now, in order to do a times 10 to the power, you can put a letter E, and then put the power after it. So if you want 1.2 times 10 to the 3, 1.2 E3 will be 1.2 times 10 to the 3. Okay, if you've got paper, I suggest do it on paper. Graph paper would be fantastic. And then use your graph to describe how the speed of a planet depends on its distance from the sun. So you'll be able to work out how the distance or the speed depends upon the distance. We've then got question 3, so work out some details about the orbits of some satellites. So very similar, but this time you've got to add the radius of the Earth, which is 6,371 kilometers, to the height they have. So that's 500 kilometers off the Earth, but from the center of the Earth, that would be 6,871 kilometers. And you've got the orbital period already in seconds, so can you calculate the radius, the distance it travels, and then you're going to calculate the velocity of them and draw another graph. Now, I'd really appreciate it if you could take some pictures of those if you've done them by hand, upload them to the assignment. If you've done them on Excel, upload the Excel sheet, that's absolutely fine, and I can have a look at that. I want to give you some feedback on this task. If you've got any questions, you know where to contact me. So let's go through what we've covered again in this lesson. So recall the factors that affect the strength of the gravitational field. Explain why G has different values on different bodies in the solar system. Describe the orbits of moons, planets, comets, and artificial satellites. Explain why the velocity of a planet changes even if orbiting at a steady speed. Describe how changing the speed of an orbiting body affects its radius. And explain how the radius of a stable orbit is affected by the orbital speed. Okay, so lots of really, really complicated physics there. Hopefully you've understood it. Like I say, anything you don't understand, make sure you're emailing that science email address and we will get back to you and hopefully help you with understanding it. So thank you very much for listening in, ladies and gentlemen. I hope that has gone okay. If you have any feedback for me, you can always let me know through the usual way. Okay, thank you very much.